Our speaker is Dolores Knipp. Dolores, after a career in the US Air Force, joined the Aerospace Engineering Science Department at the University of Colorado in Boulder in 2009. And she's also Senior Research Associate with HAO. Her scientific focus is to try to understand the Sun geospace system, with a particular interest on how it affects the low Earth orbiting satellite drag, which is what she's going to be talking about today. The title of the talk is Satellite Drag, When Human-Made Projectiles Stay in Orbit and When They Don't. So go ahead.
Thank you. It looks like I'm attached to this mic. Maybe. That would be good. And a pointer. All right. My background probably suggests that I live in a world of applied science, and that is the case. I have the great good fortune to actually be working in two institutions, the Aerospace Engineering Sciences, where engineering and sciences are in fact juxtaposed by name and by practice, and also working here at HAO a few days a week, or a few hours a week anyway, when I can get away, where engineering and sciences are also juxtaposed by in practice. So what I'd like to talk about today is essentially one of the things that makes us very human, and that is our fascination with projectiles and what it is that we do with those and how that actually interacts with science. So here we go. I have an iconic view here that I just maybe spoiled by putting names in places, but it is a view of the atmosphere taken from the International Space Station, and in this view we actually get to see the atmosphere sorting itself out into regions, the place where we have the weather that we experience, the place where ozone molecules stop, for the most part, UV energy from pummeling us. The mesosphere, a place, the middle atmosphere that we really don't sense very well. And then the thermosphere, this place up here in black that looks like it is empty and maybe somehow serene. Well, I can tell you it is neither serene nor empty, and it is the place where satellites experience some very interesting dynamics. To give you a little bit of a sense of where this talk will go, as I mentioned, I do want to talk about our fascination with projectiles, and we'll do astrodynamics in 2 slides. And then we'll talk about space weather effects on satellite motion, probably some things that you know and a few things that you don't know, and then come back and look at what is the role of HAO in helping to do the specification and prediction associated with atmospheric density perturbations that very much affect our ability to locate and predict where our very, very expensive space assets are. So projectile motion, projectiles are something that we engage ourselves with for recreation, for sport, for combat, for exploration. We're always pushing something around. I've been told that when I was a child, I was great at pushing peas off of my high chair table, and that's probably the best work that I've done with projectiles. So not a person with great finesse with projectiles, so I just decided to study them. Well, one of the things that you know, either by studying them in the classroom or by having physical interactions with them, is that you need a source of energy to put a projectile into motion. And if there are no external forces acting on that projectile, it will continue in the motion in which it has been put indefinitely. It sounds like one of Newton's laws. The other thing that we know about that is that to get significant projection, we actually need to do more than what humans are capable of in terms of giving a toss or a push. We need to put chemical energy into a system that allows us to then transfer that into energy of motion and energy of position. So since the Chinese discovered gunpowder, we have been using that with great effect. Another aspect of satellite motion that is important to low Earth orbit is that the Earth's atmosphere actually exerts a drag on satellite. That place up in the atmosphere that I showed you was dark and serene actually has enough material that orbit after orbit after orbit, it exchanges energy and momentum with the satellites, and the satellites slowly lose some of their energy. But in the process of doing that and interacting with a medium that becomes of variable viscosity, what we find is that the overall reduction of energy is also accompanied by a change of energy in terms of change of form. So we reduce the energy of position, but much of that energy goes into energy of motion, which then acts with the dense material to create more acceleration to drag. Ultimately, what happens is, because of these external forces, spacecraft in low Earth orbit do not continue their motion indefinitely. In fact, what we find is that increased energy of motion results in more drag and a faster decay of the satellite, higher speeds of the satellite, more drag, and it's actually quite a vicious circle, or a vicious spiral in the case of these satellites, that ultimately decay into either, well, certainly they come through Earth's atmosphere, and some of them actually survive the trip, the fiery trip, and end up back on Earth's surface, certainly not in as good a form as in which they started. My husband was betting me whether or not I could do this talk without an equation, and I decided I couldn't. So I lost the bet. I had to have my atmospheric density versus relative velocity squared in here, because it is the roots of the most variable parts of this acceleration. So I'm giving up a beer to my husband. Okay, this is a picture that I believe Art Richmond showed yesterday. If not, he certainly provided it to me. And it's, again, one of those kind of iconic views of what the density structure of Earth's atmosphere looks like. And you might notice on the scale here in the bottom that this is orders of magnitude. We actually see a logarithmic or an exponential decay of density with height. We have here the total density and then the various constituents of the atmosphere. As Stan pointed out, above 100 kilometers, we live in a mostly oxygen atmosphere. At about 100 kilometers, we move out of the fully mixed regime and go into a regime where there's diffusive separation. So the heavier molecules get to sit near the bottom, the lighter molecules get to bubble up. Now, this is a great graphic to just get you started, but if you want to go around and visit various locations in the on Earth, what you will see is that this general behavior applies, but when you actually start going and looking at what does the density of the atmosphere look like at various levels, you find that there is a stratification in the lower part of the atmosphere that is very much associated with the temperature regimes, which are associated with basically the Hadley cell convections, or cells that we heard this morning, about this morning. And I will just point out to you that as we march from the surface, sea level, up to the tropopause, if we put these in nice SI units, by the time we get to the tropopause, we have lost 90% of our density. And I keep going. This is what I use in class to teach, and so I decided that it would be just easier to start putting these things. We're going from kilograms per meter cubes to grams per meter cubes, milligrams. Pretty soon up here we're at nanograms per meter cubed and picograms per meter cubed. And it is in this regime that Earth's low Earth orbiting satellites operate for the most part. This is their re-entry regime. And what you will notice here is that the structure is very different. It is dominated, this is, by the way, 12 UT, it is dominated by the heat input from the sun. And so we see here the density upheavals that are associated with the sun shining on the atmosphere, a couple hours delay, and you see that the highest densities where satellites operate are going to be in the early to mid-afternoon. This will come back in a moment. So, a moment for history. Projectile motion, Sputnik 1. It turned our worlds. It was part, actually, of HAO's history in a way that Tom talked about yesterday. One of the things that was going on is that scientists, all atmospheric scientists and many engineers, were fascinated. They were listening to Sputnik. They were measuring the orbital period, how long it took to go through and come back to the same location. Sputnik was launched in '57, July 1958, part of one of the largest solar cycles we've ever seen. A huge geomagnetic storm. This is the linear version of the KP index. This is as high as it gets. AP of 400, KP equals 9. And what Hakia, who was one of the first atmospheric scientists to actually work with satellite drag, noticed was during that storm, the satellite accelerated. It was going faster. So its orbital period was changing very rapidly. And then after this puff up in the atmosphere, that's what he figured out, had essentially subsided, it went back to its more normal acceleration. So I'm not sure if at that point the term satellite drag had been coined. It was at about this time that we actually started using that terminology. But what we did learn very quickly from a single satellite is that the atmosphere does, in fact, respond to geomagnetic storms. Satellites respond to geomagnetic storms, and they're somehow all connected. Now, in case this isn't sufficient for you, let me fast forward to about 15 years ago, where a colleague of mine who taught at the Air Force Academy had an incredible citizen science project. He managed to convince kids all over the world to shine the mirrors that were eventually attached to 3 balls, 3 satellites that were taken up either in the space shuttle or launched from Kodiak. The 2 that went up in the space shuttle got kicked out the back end, toss it off the shuttle, and watch. And watch we did, or listen. The little kids, and some not so little kids, waited for these satellites to come around at night, and you could see the glint of the sun, and you could start making the measurements associated with orbital motion. And of course, NORAD and NRL and various other agencies were also very involved. And what we eventually came up with over the course of about 400 days was that this satellite that had started out at 400 kilometers slowly lost its positional energy, gave it up mostly to kinetic energy, and 400 days down the road, in they come. At least that was Starshine 1. Starshine 3, I think, was on orbit for a little bit longer. So we can start to get a sense that what I told you was true, that these satellites start to change their speeds, they start to change their position, they're coming down, and their speeds as they come down actually increases, which we go off to my obligatory equation, means speed is increasing, the drag is increasing, the death spiral begins. Watch out below, because not everything burns up in the atmosphere. Let us go back to September 5th, 1962, to this little town on Lake Michigan, Manitowoc, Wisconsin, and see what happened. Here is the marker where a 20-pound or 9-kilogram chunk of Sputnik 4 made it through the atmosphere. Okay? The policemen who were on duty early that morning thought it was a piece of junk that had fallen off. They come back a couple hours later, see that it's still on the road, try to pick it up. It's too hot to pick up. They kick it off to the side and go, what was that? Some checking, because apparently we knew that this thing had broken up all over central Canada. Some of it landed in Lake Michigan. Got a hold of NASA. NASA comes, picks it up, makes a cast, makes a couple of casts, hands it back to a combination of DOD, CIA, who take it back to the Russians and say, essentially, keep your toys in your own backyard, please. Some conversation like that went on. Okay, so you might imagine that I believe it's tomorrow or the next day there's going to be a wild Sputnik Fest. They have it every year in Manitowoc, Wisconsin. Okay, now, humor now, but it really did rattle the nerves of folks who were in the business of thinking about what the other side was doing and how much damage they can do. Recently declassified report from RAND, the date is October 1965, and the title is On the Prediction of Satellite Orbit Decay and Impact. So they started that study back in 1962 or shortly thereafter to figure out what capabilities we had to do these kinds of predictions. Guess what? We're still funding that kind of work. And when I'm not here, I'm writing a proposal that goes with a multi-university research initiative to do exactly this, and it's due next week. Okay, more. This didn't stop. 1979. Another big solar maximum started in 1978. In comes Skylab. More. 1997, January, in comes the remains of a Delta rocket, I believe. And since then, or in the intervening time, there have been 67 other documented debris landfalls, and that's only in the places that humans actually live and go and look around. So all this part of the world covered by ocean, in total, has probably received about 6,000 tons of human-made material that have survived the fiery reentry and chewed up a whole lot more that didn't make it. Okay, the US Air Force, NASA work hand in hand to do this forecasting now, but their job is not easy because when we started out in 1960 and there was a Sputnik 1, 2, 3, or 4, and now we progress our way through seeing how much stuff is there. And that stuff consists to a small degree of active operating spacecraft and to a large degree of space junk. This distribution of that space junk looks something like this. We actually track those 22,000 things that are about the size of a softball. We wish we could track these 500,000 things, and maybe we will, given computers and the improvements in computers. We will probably never track this. But these things that are only about the size of a period or so in real life, can do incredible damage to windshields of International Space Station. We actually bring spacecraft back and determine if we have to repair any damage that's associated with those impacts. The reason the impacts are so dangerous is because the interactions are at hypervelocity, typically about 7 kilometers per second. This is a marble-sized 1.7 gram aluminum sphere that has been shot into a block of aluminum. The instantaneous shock and the pressures that are associated with those are generally larger than we actually experience at the center of the Earth. If we could go there, it's instantaneous, but you can see that the damage is not only to the exterior, but the shock wave has propagated through and actually separated the bottom material. More reasons that we are concerned is we have to keep track of all of this stuff, that 22,000 things, that's a lot of mass up there. Some of these things are in some orbits that are very popular, and the reason there are so many things in some of these orbits is because there were a lot fewer things until something blew up. Those things that blow up very often occupy the same orbit, and so some places are getting very, very congested. Those are the lanes that we actually have to operate. And here is an indication of the number of objects that can be tracked. And this is the linear growth of what that looked like. We realized in 1996, we really have problems here. NASA agreed, other agencies agreed, all kinds of rules put into place for mitigation. Bring your stuff back when you're through playing with it in space, that sort of thing. But then there were an anti-sat experiment from China and a just oh darn Iridium Cosmos collision in 2011 that repopulated a very large portion of these things, these regions. The real problem with this is that in trying to keep track of these things, which we do by radar, by GPS, by lasers, you name it, we try to keep track of it. We have what would be the unperturbed orbit, what we predict will be the motion coming down, speeding up, based on a model, and then what the real atmosphere actually does. So we have a tremendous amount of planning that goes on for all of these reasons: mission planning, re-entry prediction, on-orbit lifetime, collision avoidance. We actually use some of these orbiting bodies to help our models improve by monitoring the density. All of this is going on in the background, and I will just bring up one item here. There is a conjunction analysis risk assessment, a conjunction assessment risk analysis that has been issued for the IRIS spacecraft for tonight, tomorrow morning, where there is a piece of debris that puts the risk into essentially the red category. IRIS does not have on-orbit propulsion, so we just have to hold our breath and hope. Okay, what are HAO's contributions in this? I really like to get up close and personal. This is something that Art Richmond showed yesterday. This is the region where the group that I work with called AIM here in HAO actually does its work. I will skip over these because I think you're aware of these. And I will, let's see, will this one click? Yeah. So this is an earlier version of one of the magnetospheric models that has now been much better coupled. But what we are doing is, in this image, we were essentially seeing how the magnetosphere is responding to forcing from a coronal mass ejection. You're seeing the last closed field lines here. Those closed field lines are field lines that can carry energy into the auroral zone. When that energy comes into the auroral zone, the work that Gong Lu has done basically shows that that energy does not stay in the auroral zone. It propagates out in significant waves or pulses of neutral density. And I will move on here to actually show you what that looks like in still, because that's the way I use this kind of material in my classroom to reveal that these pulses come out. Pulses come from the other atmosphere. They intersect near the equator, and you can have tremendous density upheavals that affect satellite motion in a very, very big way. HAO is also contributing by making significant new measurements of neutral winds now in daylight. That has not been, the first time this was done was in 2011. Most of our neutral wind measurements to help with our models had been made in nighttime only, but Shen Wu has been able to figure out how to put a Fabry-Perot interferometer at 40 kilometers where the scattering of sunlight is small enough that we can actually measure the neutral winds. And then that information is going in to help constrain the models that Stan just talked to you about. I will show you one more image that Stan showed. He was talking about the fact that Early on, Ray Roble and Bob Dickinson had predicted that there would be, in addition to responses from energy coming in, there were going to be responses from energy going out. I want to point out that these very, very quiet, this recent quiet minimum that we have experienced has actually in some ways been a real boon to our field, because we have been able to determine what the response is to the forcing from below. And you've seen this image before. I will just play through here to show you what happens when gravity waves generated by a hurricane, a tropical storm, are actually impacting the lower thermosphere. Not only do we have this, but during the very quiet time, we were also able to find out that lunar tides are having an effect on the atmosphere. There's all kinds of tidal motions going on. And I will start to summarize here by bringing up one more image to tell you a little bit about what the interaction is that's going on between my department, CU, and HAO. I think you've seen this image before. It's a cartoon from NASA that shows where the energy is provided to the energetic particles right here at this reconnection point. That energy drives into the auroral zone. But one of the things that we have not yet done very well in our models here at HAO is specify what the height-dependent nature of that energy deposition is. We get to see it in the visuals that the astronauts take. So some of the work that my graduate student Ryan McGranagan and I and Stan Solomon are doing is we are now reworking some of Stan's codes to allow us to take the measurements from DoD satellites that tell us how much energy is associated with the individual particles coming in, and we're reconstructing the conductivity of the atmosphere. We're figuring out how able the atmosphere is to carry currents, and that will help us understand what the energy distribution is from those currents that are coming as a result of magnetic reconnection. So to give you a very quick summary, humans have been involved with projectile motion for a very long time. We've been about 60 years with our projectile motion into space. Very good news, sometimes very bad news. Some of the bad news right now with this cooling that I had mentioned to you is that the space junk that would normally fall out in these very quiet times is actually staying put. So it's a bit of a challenge for those of us who are trying to figure out what's going to collide when. What goes into space often does not stay there, or at least not for very long. There's a significant need for tracking and specifying, forecasting the state of projectiles. The science meets applications here at HAO. And HAO has been partnering with a number of the agencies to try and move this science forward, and is very, very engaged with educating the next generation of scientists and engineers. And I have been a really proud participant and recipient of that interaction. Thank you.
Yes.
Thank you, Dolores, for that enlightening talk. Could you comment on the use of CubeSats vis-a-vis the orbital debris issue?
Good news and bad news. There's actually a study I was looking at last night where NASA was considering what kinds of information can we get that will help us, and there are, of course, plans. These CubeSats are free-floating, so the bad news is that they will probably actually add to some degree to the satellite debris problem. Most of these CubeSats are longer lived than their missions. They're not rad hard, so that they're going to be up there for a while. There are some CubeSats that are actually they're working on, you know, some kind of a deorbit plan, but those deorbit plans actually take years. So they are going to be a contributor to the space population. We are hoping that the new kinds of measurements that can be made, especially if they can be made in lots of places, even if they're not the best quality, can be put into data assimilation where you can use measurements that might not be of the most exquisite kind, but give you enough information to find large patterns. So I think the prospects are exciting, but it will, there's a lot to be learned, I think, yet in terms of how effective we'll be able to be in terms of miniaturizing some of the measurement or some of the little observational platforms that need to be made. But it's an exciting time. I'm in the aerospace engineering department. We work with LASP, our students work with LASP to see just what can we pack in.
Time for one more quick question, and then we're off to the break.
You didn't talk anything about mitigation. I know in Europe they're busy throwing tons of money at all kinds of wacky ideas to try to go up and grab some stuff and bring it back down.
Yes, you're right. There was not enough time to talk about mitigation. It was about 20 years ago that NASA and most of the space agencies of the world realized that mitigation is something that we have to engage in, because if we do not, the movie Gravity will become a kind of a daily occurrence, or may well prevent us from effectively operating in space. But you're right, there are all kinds of interesting ways to go collect that stuff. And my colleagues in aerospace engineering are actively working on those.
Let's thank Dolores again. That was a beautiful talk.